is called analyzing protein similarity by clustering molecular surface maps. And the presentation will be given by Karsten. Karsten, please go ahead. We're looking forward to your talk.
Yep. Where was it? Yep. Here we go. So thank you, Stefan, for the kind introduction. As already said, I'll be talking about analyzing protein similarity by clustering molecular surface maps. Let me give you a small motivation of this topic. So understanding the relationships when you have one or multiple protein structures is quite hard. So let's say you have given these two proteins on the right. They are different in some kinds of ways. When you look at, let's say, the sequence, it's kind of easy to find, but when you look at them visually, it's not that obvious where the differences are. So you can see that in the black circle, for example, where a small difference occurs. Thing is, when you look at the sequence, you will see many things that do not really contribute to the function. The interior may shape the outside of the protein, but the really functional important parts are on the outside. So, but it is like that most existing approaches do not focus on the surface where the really important things for the function of a protein are. So our approach therefore wants to have a look at the protein surface, compare surfaces of two or many more proteins, compare them, and then have a look if a visual comparison is enough to estimate functional similarities in such proteins. Just give me a kind introduction to how similarity in proteins works. So typically it all starts from the amino acid chains. All proteins are built out. So they consist of one or multiple amino acid chains. When they are similar, this typically leads to a similar chain folding. These fold in 3D in a specific kind of way determined by forces and other properties. Then this, of course, leads to a similar 3D structure, which in a visualization leads to a similar visual appearance. But what has that to do with function? All of these three first properties can lead to similar surface properties. Not necessarily, but statistically it could. And this, of course, then leads to a similar function. Our idea is now, how do these two relate? So to start with that, we first need a method that is able to depict the surface without concentrating on an interior and without visual clutter and stuff like that. For that, we decided to use the method by Krone et al. Called molecular surface maps. The method was first presented on VIS 2016. The idea was to take a solvent-excluded surface of a protein, blow it up to a sphere, and then map it onto a map, of course. This introduces a little bit of distortion, but we hope to show that it is more or less negligible for our use case. We added some adaptations to it, which will become relevant later. Well, what do we want to do with that? First, we have to align input proteins. That's just a small pre-calculation because we do not want that rotations and translations of proteins come in our way. So we align every protein that we are inputting in the same coordinate system. This is PCA based, so we just do a principal component analysis of each input protein, and then we rotate and translate it so that it is in the origin, and the x-axis is the first principal component is mapped on the x-axis and the second one on the y-axis. With that, we calculate the already mentioned molecular surface maps. We do this with 3 different map types. So here we use the B factor, the temperature factor, the hydrophobicity, and a height map. These represent 3, let's say, scales of a protein surface. The B factor is a per atom quantity, the hydrophobicity is a per amino acid quantity, and the height map is more or less a topological quantity that depicts the distance to the center of the protein. Additionally, there comes our first modification into play. We calculate value maps that have no color mapping applied, that so that we can use them later on in our calculations without the, let's say, false color mapping on top of it. When we now have these maps, we want to cluster them and have a look at it, how they relate, well, at first visually, and then have a look if they're similar functionally. So for that, we take the maps that we just calculated, which are just PNG images, and compare them by first calculating some feature vectors for each of the maps, and then using these feature vectors to calculate distances between the maps and do our hierarchical clustering with that. And finally, with a hierarchical clustering, we of course have a tree structure. So we just want to render that tree structure. Additionally, some selected proteins for further reference, and we want to enrich that with additional information. So what is a method that we can use to compare some images? So we have these maps, which are basically images, and we have to compare them. But in our case, a protein, well, is more or less a round shape. Not always, but it comes close to it. So the maps we want to look at have, so the comparison algorithms we want to have a look at should be able to cope for some kinds of distortions. So although we aligned the proteins, it could be that they're rotated a little bit against each other and so on. So the map comparison algorithm should cope for that. We do this by posing some restrictions to our feature calculation, which is here then done with these restrictions listed here. So it should be invariant under rotation, translation, and mirroring. Especially the periodic translation is of importance, which you see on the top right here. That could happen to the maps when the proteins, rotate a little bit, or what's also really important is the mirroring part, as maybe the principal component analysts could flip the sign, and then the mirroring is of importance. Yeah, these are prerequisites to feature calculations and the comparison. So we decided to test 3 different feature extraction methods. The first one was the image moments method by Who. We switched the third moment they use with the one of Lasser et al. Because it was kind of dependent on the other moments, which results in a 7-element feature vector. Then we used the color moments. That calculates the mean, the standard deviation, and skewness for each color channel. And which results in a 9-element feature vector, and the mobile net v2, which is a, well, full-fledged CNN that is pre-trained for real-world image data. but we only use as part of it to extract the feature vectors. The whole net is capable of far more than that. And as you can see, the feature vector is quite large in compared to the other ones. What's remarkable here, we only use the value maps I explained earlier, only for the image moments and the mobile net. As the color moments heavily depend on the color, we have to first apply a color mapping to them to use them with color moments. Otherwise, the feature vector would get far too small. So now that we have these feature vectors, we can just compare them. So we do this by just doing an Euclidean distance between the feature vectors, then we get a distance value, and that's it. So then we have the distance between two maps or the proteins they represent. Out of this, we construct a UPGMA tree, so which is a hierarchical clustering. We decided to use an UPGMA tree because it's a familiar method for domain scientists. They typically use it for, let's say, ancestral studies of proteins, so they can look which proteins are related to each other and so on. It's far easier to do. So the properties of these UPGMA trees are that the distance between two nodes is encoded in the height. So as you can see here, the distance between A and B is 10. And the height of the node connecting them is 10 divided by 2. And that is a property for all of the distances here. And of course, there is a formula for the distance between a node and a whole cluster, and or between two clusters. On the right-hand side, you see the formula for the distance between two clusters, which is just the sum of the pairwise distances. Now that we have a clustering in a UPGMA tree, or no, we don't have the clustering yet, we just have a hierarchical structure for which we want to apply some, insert some clusters. The final clusters are then found by just setting a cutting threshold at a user-decided distance. So let's say, well, the user says proteins in a cluster should, let's say, a distance of 8, a maximum a distance of 8 apart. And then we put in this clustering threshold, as you can see in the top right. And this results in multiple clusters. There you now have 2 clusters, for example. With that, we then move on to our visualization application, which consists of basically 3 views. On the top, you see the clustering with some interaction capabilities, so you can zoom, you can hover over nodes to see the maps larger, and you can click on all the maps at the bottom to retrieve the original protein surface on the views on the bottom. So this is for just direct comparison of the proteins. Those views are linked, so when you move one of the views, it will move in the other, so you can see, look at it always from the same angle. Yeah. With that, let me just come to our results. We had 3 test data sets. The first one consisted of 10 proteins, which were hand selected and consisted of 2 clusters and 1 outlier. This is the data set you can see on the right. Especially in the top cluster, you can see some mirroring and some flipping going around here. So we intentionally decided them to be similar so that we can make a guess if our method really works as intended. Then the second data set are 50 enzymes that we selected from the Brenda database. These are for more checks, and then a large data set of 1,000 enzymes for performance investigations and so on. Let me just start with the first data set. So this is the clustering of the 10 protein data set. So as you can see on the top left, we have the height map clustering of the mobile network V2. There you can see there are 2 distinct clusters and 1 outlier. So the outlier is somewhat clustered in the middle, but it's clustered rather late. And that's more or less what we wanted. So these are also the correct ones. So the ones with numbers below them are 1 cluster. 4i38 is the outlier, and the other ones are the other cluster. So this is the desired result. The same goes for the hydrophobicity maps for the mobile net V2. But then we come to the B factor, and there we can see that one CIO, for example, was not clustered correctly or really, really late. That is not desired. And this is behavior that continues to show when we have a look at the other clustering methods. For example, the image moments, which performed rather poorly. So as you can see there, the clustering between the proteins with the number code below them is not kept. And the clustering of the other ones is also not kept. So that's quite bad. And it clusters 108M as outlier, which it is clearly not. So it works a little bit better for color moments. So there you have a rather perfect clustering. It looks better than MobileNet V2 because everything is clustered earlier. But this is mostly the case due to the fact that the feature vectors of the MobileNet V2 are really large, and you have some base level distance encoded then in there. So you just have this ground distance where you have to start at. And then what we are also capable to do is to combine the protein, the feature vectors of multiple maps. So on the bottom right, we use the height map and the hydrophobicity map together by concatenating feature vectors. And we got a result that was also working and a little bit more desirable, as how their 4i38 was merged last as compared to, let's say, the top left, where it was not merged last, but then the other cluster was merged last. So yeah, it could add to a better clustering. So let me just quickly compare the methods. We executed this for all of these methods. I could not show all of the maps here, all of the clusterings here, but as you can see, the MobileNet V2 mostly keeps intended clustering. The only downside is that the B factor maps are generally unfeasible, maybe because they are too noisy, maybe because it's more, let's say, of a generic value that does not really add to the function of a protein. But the MobileNet V2 works quite well. The color moments work quite well, with the exception of the B factor, and the B factor pollutes the combination of the maps. So when you combine all three, the B factor somewhat destroys the result. So therefore, for the further tests, we decided to only use the MobileNet V2. And for that, we want, for the further tests, we would like to have a ground truth that we could compare against, which would be a functional ground truth. So we had a look at the so-called enzyme classification, which is a classification for each enzyme that is a number code that classifies the enzyme based on their function. So the first number in this number code, which you can see on the top right, is the general type of the enzyme. The following two numbers could stand for the donor and acceptor of the reaction they accelerate. And the fourth one are just further granularities. So we used this number code and compared those number codes to retrieve a distance. And with this distance, how we got this distance, you see here, when the numbers were matching, the distance were lower and so on. You see this table here. Additionally, we use a TM score, which is another distance measure based on sequential and atom-atom distance, to further see if our distance measures were more or less working correctly. So this leads us to our 50 protein data set, where we encode not the clusters, but the distance matchings. As you can see, yellow is a pretty good match as the distance is 0. So most of the direct matches match at a distance of 0. So this is a perfect match, and that should be like that. There are areas where it's not perfect. So, so here at left it is. But here are areas where it's, for example, not perfect, but we match rather late. Yeah, I know I'll run out of time. We match rather late, and that's quite expected. We match rather late, but the distance between them is at 1, which means they're rather close functionally, but not perfectly like it. So that's a good thing. Then let me switch over to the comparison with the TM score. Same coloring scheme, but here you can see now that the TM score says the distance is quite high, which was unexpected, and that we that we are in these cases better than the TM score, which is just a purely geometrical measure, and we were better than at clustering them, visually. So I unfortunately have to skip the 1000 enzyme case because I ran out of time. Then let me quickly come to a conclusion. We presented a comparison of protein surfaces based on the molecular surface maps. The approach delivers good results for the MobileNet V2, and despite the distortion introduced during the map generation step, it can be better than the TM score when looking for functional similarity. And in the future, we plan, let's say, a less random input data set, because we just randomly selected them from a database. So we talked with our project partners about that. And of course, which is far more important, we want to have a look in a self-trained convolutional neural network to get even better results. So thank you for your attention. Are there questions? If we have the time, I overdid a little bit.
Yes, thank you very much for the nice talk, Karsten. There's quite a lot of interest. We're a bit pressed on time, so we may not get through all these questions, but I'm sure you will stick around and answer them in the chat. So the first question we had was from Xavier, and he wonders whether there was any reason for not using classical alignment algorithms such as CE align or TM align.
The problem with the classical alignment algorithm is, so if you wanted to use alignment algorithm, we would like to have used the standard which would have been used when looking at proteins, which would have been, let's say, minimizing the root mean square deviation and getting then a rotation matrix and translation out of it. And but that would have led to emphasizing one distinct protein that we have to rotate against. So therefore, we used a method that did not, well, let's say, add that weight to one of the, let's say, randomly selected proteins. And yeah, that was the main reason behind that we switched for such to such a unconventional alignment method.
Thank you very much. I fear we are unfortunately out of time. There are plenty of interesting questions in the chat, and I hope that there will be some lively discussion. Thank you very much again for.
I'll try to answer them. Thank you very much.
Now we move on to our next presentation in this session. And this is work on the real-time visualization of 3D amyloid-beta fibrils from 2D Cryo-EM density maps. And this is work done at Ulm University by Hanna Kniesel, Timo Ropinski, and Pedro Hermosilla. And Hanna will be giving the presentation. So please go ahead, and we are looking forward to your talk.
Thank you very much. Thank you very much for the kind introduction, Stefan, and hello to everybody watching. I hope you can see my screen now and you can hear me well. So as Stefan already nicely introduced, I will walk you in the following through our real-time visualization of amyloid-beta fibrils from 2D Cryo-EM density maps. So here, let me start off with the motivation of our approach. So amyloid-beta fibrils are the result of an accumulation of misfolded precursor proteins along an axis, and those then form beta sheets, which are repeated along this axis. The structure can be nicely seen in the figure below, which I took from a publication from Knowles and Mazenga from 2016. And here you can nicely see the repetition of the beta sheets along this fibril axis, and you can see that the fibril forms this helical structure, so it has this twist value. So also the amyloid-beta fibril is also already known for playing a crucial role in the Alzheimer's disease, as well as diabetes type 2, just to name a few examples here, but its function is still not fully understood. And based on the insoluble nature of the fibril, methods of structure determination are rather limited. A nowadays well-established method is the cryo-electron microscopy. And here researchers collect multiple of thousands of micrographs from a cryo-electron microscope, and they input those into a helical reconstruction. And this outputs then a volume slice of the fibril as a density map, which you can see over here in the slide, and also helical parameters of the fibril, like the twist and rise of the fibril. Using those output parameters, researchers can then use a 3D visualization and molecular mapping to explain the features. And based on this explanation, they get then a further insight into the structure of the fibril and so into the function of the fibril. So our approach here mainly focuses on the suitable 3D visualization of the fibril. The problem with that we're currently facing is actually the progress in Cryo-EM, because the resolutions are getting better and better, and hence data set sizes also increase. So if we have a look at an example here, the position at the electron microscopy database with the accession number 3132, which was published in 2015, has a resolution of 7 Armstrong, which then consumes a memory size of 74 megabytes if we consider a memory consumption of 4 bytes per voxel. And this is usually actually the standard over here. Then if we have a look at the deposition with the accession number 4452 from 2019, we see that the resolution has become much better with 3.3 Armstrong. Also, the dataset sizes has grown to 1.2 gigabytes, which is just much larger as the one from 2015. And in the future, we'll get closer and closer to this atomic resolution, which is everything just below 1.2 Armstrong. And also, the researchers usually need to compare multiple fibrils side by side, so there we also have an increase of the dataset sizes. Another problem we're facing is actually the uncertainty from the reconstruction process. So over here you can see a density map, which we got from the reconstruction process. And here, high electron densities relate to the presence of atoms and are depicted in white. And the low electron densities relate to the absence of atoms, which are depicted in black. But as you can see, those areas, they don't have a strict border, but they're rather connected through those smooth grayscale gradients. And this is where the uncertainty is actually encoded. The uncertainty comes from the flexible nature of the fibrils. So we get small variation of the atom positions between the different cross-sections of the micrographs, which we use for the reconstruction. And then we also have the usual noise sources like the beam-induced movement, ice contamination, or just the usual noise in the electron microscope. And those then add up to this uncertainty in the density map. So to summarize, we're facing two problems here. The first one is the increasing GPU memory consumption based on the improved resolutions. So therefore, we propose an approach which does not increase the memory consumption for variable fiber lengths. And the second problem we're facing is the neglection of the uncertainty in the 3D visualization. And therefore, we propose a simple visualization of the data uncertainty directly in the 3D model. Further, our approach is able to implement beneficial features like an adaptive twist value, which can be important for the researcher to fine-tune helical parameters he got from the reconstruction software. And then also we're able to achieve high rendering quality already for low resolution data. So to implement our approach, we used a standard ray margin approach and extended this with the prior information of the fibril we already have. So with prior information, I mean the twist value of the fibril. So based on the repetition of these beta sheets along the fibril's axis, we're able to use this density map, which we get from the reconstruction software. And then we apply a transformation of texture coordinates according to the twist value of the fibril. So on the left, you can see just the standard approach of the ray margin, where the view ray is a straight ray through the volume. And on the right, you can see our adaptation, where this ray then gets twisted according to the fibril's twist value. And this is applied based on the transformation of the texture coordinates. So here we can say that the core of our approach is actually this texture mapping. First, we start off with rendering a bounding cylinder, which is aligned with the fibril's axis, and then just apply some simple basic texture mapping, where we take the center into account and normalize the coordinates from world space to texture space. But special here is that we're only using the XY coordinates in world space to transform the sample into texture space. And we do this because we're basing our approach on the 2D density map from the reconstruction here. So next step would then be to take the prior information into account. So we need to rotate the sample in texture space. And therefore we need to determine the angle alpha here. So what we do is we have the sample in world space and project it onto the fibril's axis. And then we normalize it based on the total length of the fibril. So we get the value in between 0 and 1. And also we still have this total twist value of the fibril from the reconstruction software. And we use the, and we interpolate this value then based on this level of height of the sample regarding to the whole fibril size. So next, we also introduce a minimum density threshold. We use this to determine the outline or surface of the fibril, and this is just pretty similar to the isosurfacing. So over here, you can see that we made the minimum density threshold adaptive, and also we made the twist value adaptive. And again, this is pretty beneficial for the researcher, so he's able to fine-tune the parameter of the reconstruction software. And as you see, if we zoom in, we're achieving a rather high rendering quality. And this is also the case because we're extending the ray margin with a binary search. And what we do here is we start marching the ray with a constant step size. This is just similar to the standard approach. And then as soon as we step into the volume, we start to apply a binary search with just a few iterations. And so we're able to determine a more accurate intersection point of the view ray with the volume. And over here, you can see what that then looks like. So first, we didn't apply the binary search. And if you zoom in on the right, you can see those artifacts appearing. And they become even larger if we increase the twist value of the fibril. But if we're applying just a few iterations of the binary search, you can see that those artifacts totally disappear. And we can even further increase the twist value without generating those artifacts. Well, as you've already seen in the previous video snippets, we also apply state-of-the-art illumination techniques. We do so to enhance the perception of the fibril structure, which is pretty necessary for the researchers. So we first apply hybrid ambient occlusion. We further add the diffuse component of the Fung illumination model. And lastly, we apply shadows. Then to visualize this uncertainty from the reconstruction process, we propose to render a semi-transparent code. And therefore, we introduce a second minimum density threshold and define the sample points PT1 and PT2. So PT1 is the sample point determined by the intersection of the view ray with the solid fibril. And the solid fibril is determined by the first minimum density threshold. And then we have the sample PT2, and this is similar, just that we're now having the intersection with the semi-transparent code, and this is defined by the second minimum density threshold. So we assign color values to both of those samples and compute illumination. And then based on the length of the view ray between those two intersection points, we interpolate color values and illumination values. And we further scale this interpolation value, so the length of the view ray between those two intersections, with a sigmoidal function, so the results become more realistic. And over here you can see this in action. So again, we made the second minimum density threshold also adaptive. To evaluate our approach, we first compared it to volume rendering. Next, we conducted a user study to evaluate the interpretability of the semi-transparent code. And lastly, we conducted an expert interview. So let me start off with the comparison to volume rendering regarding the rendering quality. And what we did here is we rendered this fibril, which you can see on the right. First with a volume renderer. The volume renderer was based on the VTK software packages from Python. And then we compared this to our approach. And you can see just small sections of the fibril on the right, so you can see them more in detail. So what we did is we changed the resolution of the volume. So over the rows, we changed the resolution in XY direction, and over the columns, we changed it in the Z direction. And here the Z direction is the length of the fibril. So our approach only uses the 2D density map. So we're only having this one column over here. And as you can see, for a low resolution in Z direction, we get those artifacts in volume rendering. And this is also the case if we have a low resolution in XY direction. Those artifacts appear based on the trilinear interpolation of the volume rendering. So we would need to simultaneously increase resolution in X, Y, and Z direction to generate a sufficient result. On the other hand, you can see that our approach generates high rendering quality already for those low resolutions, which is pretty beneficial for the inspection of the fibrillator. And we're able to generate those high volume renderings even though our memory consumption is much lower. So over here, we're considering a memory consumption of 1 byte per voxel. And if we're having a look maybe at the largest volume over here, you can see that for the volume rendering, the memory size increases significantly if the length of the fibril increases. So the second row of the marked area right now is the long fibril, and the first row is just a section of this fibril. And this applies for the standard approach as well as for sparse memory. For sparse memory, we just save occupied voxels of the volume. You can see that our approach does not increase the memory size or memory consumption, even though we increase the length of the fibril. And you can also see that the memory consumption is much lower. It is actually even lower than the sparse memory for the small fibril section. And this becomes even more clear if we're having a look at the memory consumption of 4 bytes per voxel. So again, the largest volume. Here it uses already 16 gigabytes for the standard approach, which is still 3 gigabytes for the sparse memory, but our approach just needs this 1 megabyte of memory here. Based on this little memory consumption, we are also able to outperform volume rendering regarding performance. So with performance, I here mean the time per frame in milliseconds. And here we compared our approach to, again, the VTK-based volume renderer and also a volume renderer which is based on the in vivo framework. And as you can see, the in vivo-based volume renderer is not even able to generate a volume which has more than those 4,096 slices. But the VTK volume renderer is able to do so. So he's able to render large volume renderings, but only at cost of the time per frames in milliseconds. But on the other hand, you can see that our approach performs rather constant for all the different volume sizes. And this is the case because we're just consuming this little memory that we can access it directly from the cage. So we further conducted an online user study to evaluate the interpretability of the semi-transparent code. And therefore we showed 23 comparisons to 31 non-experts. And those comparisons were similar like the one you can see over here. So a similar fibril with a different depth of the semi-transparent code. And then we asked them to choose the image with the thicker or deeper transparent code in the marked area. To generate different visualizations, we used 3 different density maps and altered twist values in uncertainty, and well, that's it. So we got those 23 comparisons. The results of those could show that the participants reached a median accuracy over 100% for all the tasks, as well as for each of the different models separately. And this lets us conclude that the relative differences in the uncertainties can be interpreted rather well. So lastly, we conducted an expert interview with a researcher in the field of amyloid-beta fibrils. And he underlined that the memory size will further grow and that they already clipped the volume data to decrease the file size, which further supports the motivation of our approach. He also highlighted beneficial features like the interactive thresholds and twist value, and of course the uncertainty visualization. But for more insights, I would here refer you to the paper. So, as a final conclusion of the whole approach, we offer the visualization of long fibril sections with significantly lower memory consumption. We're able to generate high quality renderings even for low resolution data. And we're achieving the interactive performance also for large volume renderings. We implement beneficial features like the twist value, the interactive twist value, and lastly, we proposed a visualization of uncertainty directly in the 3D model. So I thank you very much. Oh, wrong slide. So I thank you very much for your attention, and I'm happy to answer any questions.
Yeah, thank you for the presentation. There have been lively discussions in the Discord also regarding the last talk, and there are some questions for your talk as well. Bernhard Breim would be interested in finding out, referring to slide 10, how the twist parameter is determined or adjusted.
Let me just go back to slide 10 real quick. How the twist value is computed is just based on the reconstruction software. So this is nothing what we are touching here. So we're just taking the output of the reconstruction, which usually has this twist value of the fibril with the helical parameters, because we're applying a helical reconstruction. I hope this answers the question.
We have another question from Xavier, who asks, just for fun, did you try to duplicate the fibril and have lots of fibrils in the same scene?
That is a really good question. Thank you for that. We actually thought about it, and we definitely still want to do it. We didn't do it yet, but this is still open for future work. Yeah, definitely.
Yeah, I think the approach would be very nice for sort of instancing like visualization.
Mm-hmm.
Then we have another question by Daniel Baum. How does the 3D visualization of the fibers actually help the experts to adapt the reconstruction parameters, for example, the twist parameter?
Okay, so thank you for the question. So what they do is they apply this molecular mapping, and they also have the 3D visualization, and they compare everything against their input data. So the input data here, I mean the density maps usually. And so the output of the reconstruction software is the density map as well as the twist value. And this is just based on this helical reconstruction. So this is not always really accurate. So what the researcher can do is then just compare everything against each other and fine tune those parameters.
Let's see. I actually have a question myself, since you achieved quite high performance already. Have you also experimented with using higher order reconstruction methods, particular like Schäfer has shown in this SIGGRAPH 2019 paper? You can nowadays get higher order reconstruction essentially for free, or at least with very little overhead, depending on your exact setup. And did you do some experiments with that?
That's a really interesting question. We actually didn't do it, but we should keep that in mind for the future work. Thank you. Mm-hmm.
And I actually have one more, if I may. So now you're using a sort of, you're trying to, in some sense, emulate the kind of images that you would see from volume rendering with respect to using kind of transparency blending. Did you also think about using other stylistic choices for indicating the layering, like contours or ghosting or something like that, which could be more beneficial in showing in showing the spatial relationships there?
Mm-hmm. Yeah, that is a really good point. We have thought about different perspectives of the uncertainty visualization. We also talked to the expert regarding this. We got the feedback that the visualization of this semi-transparent code was already pretty well thought of, but there are also suggestions to improve this, like having more different thresholds and similar, so more layering and stuff like that. And we still think this is just really in the early stage of the uncertainty visualization. So there's much more work to be done to compare different approaches. Like different visualizations of contours, maybe even glyphs or something like that, just to see if that improves the awareness of the uncertainty in different ways. Mm-hmm.
Yeah. Thank you very much. Very nice work. And with that, I think we will move on to the next presentation. This work on the visual exploration of large normal mode spaces to study protein flexibility. This is an invited talk, and the authors of this work are Pierre Bedoucha, Nathalie Reuter, Helwig, Hauser, and Byška. And the talk will be given by Pierre. Please go ahead.
I hope
we're looking forward to your talk.
Yes, thank you for the nice introduction. I hope everyone can hear me and see me well. So yes, perfect. So just to give a bit about starting the presentation. Oops, and on the correct slide, perfect. So just to give a bit more context, this project was was a joint venture between two groups, so the visualization and computational biology units at University of Bergen, and also Faculty of Informatics at Masaryk University in Brno, Czechia. So from myself, I'm a part of computational biology units, so I will focus the presentation on this point of view a bit. So when I will refer to people conducting the work, I will also refer the work we conducted at computational biology unit. So to give a bit more motivation about our work, it deals with computational structural biology. So it's basically studying protein structure and dynamic.
Yeah, so sorry to interrupt you.
Yes.
I'm being told we don't see your slides. So maybe you can try to
maybe
restart the screen sharing.
Yeah, probably. Yeah. Sorry, my bad. I thought I had it, but yes, it's better.
Oh, it's working. I'm out again.
Yeah, sorry about that. So just starting again from the first slide very quickly, just so that you can see the affiliations. So everyone hear me, hopefully. And so about the motivation again, so like I said, it comes from the computational structural biology, which is studying protein structure. So you have here the building blocks of the protein structure, which is the primary structure, which is made of amino acids, as you can see here. Then the 3D organization of atoms fold into a secondary structure, forming, as you can see on the bottom, alpha helices and beta sheets, and which in turn arrange in folded state to have the final form of the protein structure. So for this we adapt a bit the biology dogma, but for structural side of things, which is to go from protein structure, so the 3D organization, to protein function, as it was a bit presented in the first talk of this session. And for this, we could use studying protein dynamics. So that's will be the focus of this talk. So for this, we to link between the protein structure and protein function, we focus at protein voids, also called tunnel or channel. As you can see here, the difference between the tunnel or the channel is basically a tunnel starts from the outside of the protein and ends inside the core of the protein, whereas a channel goes through the protein. And the protein voids, or the tunnels, are made of or are formed by the surrounding amino acids, as you can see here in red, either in the schematic or in the 3D view on the right here. And tunnel or channels are usually represented as a set of contiguous spheres, as you can see here in blue. So to go further with the motivation, I will give a bit more of an example with this visual from a paper about a ligand channel. So here on the A, you can see that we usually study the protein dynamics or using conformation as hallmarks, as you can see here in blue, gray, and red, for example, for this channel. And then to study their function, we will focus on the dynamics of their tunnel. So for example, in B, the tunnel will be the void that is inside the packing of this alpha helices. And here, for example, with the alpha helices that are highlighted in the bottom a bit, you can see motion of this alpha helices going from red to blue. And this permeates or mediates the function of this protein. For example, as you can see on C, small ligands, which are the small molecule, will be granted access to the core of the protein and be able to go through the protein or not, given the opening of the channel. So that's given a bit more details on the function of this protein, for example. So to study function and protein dynamics or tunnel dynamics, we usually use molecular dynamic simulation, as you can see on the screen. But it's a quite computationally expensive method. And also the motion or the movements of the protein are not all relevant for the function. There's a lot of random Brownian motions, as you can see here, for example. So it's always difficult and time-consuming to study the protein dynamics and the tunnel dynamics. So for this, there is another state-of-the-art methods, which is normal mode analysis, or NMA. And it decomposes the protein dynamics into oscillatory motions, which are to be considered as intrinsic dynamics or metadynamics, to describe the dynamic of the protein, as you can see with an example here on the right. So those normal modes, they form a basis set, and basically the all available motion of the protein can be a linear combination of all the normal modes that are derived for this protein. As you can see here, for example, on you have mode 7 with mode 8, and that gives a linear combination of potential motion for this protein, as you could see on the right, by combining those two modes. So the normal modes, they form a mean to classify the available protein motions. But studying the normal modes to go from structure to protein function is a complicated task, and it revolves all around the concept of normal mode analysis. So usually state-of-the-art technique is to use one mode per one mode and to focus on mainly the slow modes, so the modes that are impacting on the strong or large amplitude motion, as you could see. And state-of-the-art method is to use a 2D graph to analyze the fluctuation that are caused by these modes, with the x-axis being the amino acids. So we lose with these graphs, we lose the 3D informations. And also it becomes very quickly tedious to analyze different modes, as you could see here on the screen. So with those problems problems in mind, we devised requirements that are necessary requirements for an efficient tool for normal mode analysis. So first task would be to visualize protein-wide influence of the normal modes on the protein structure on a global scale, as you could see with this small reminder of what the global scale of a protein is. And then we have more query tasks that are either focusing on the global scale or the local scale. So for example, for the local scale, it would be to identify correlated motions of amino acids throughout the protein. And of course, to link the structure to the function with the tunnel dynamics, would be able to summarize the tunnel property changes under one normal mode or a combination of normal mode, of course. And one requirement would be also to use only one single protein structure and not hallmarks of different states or intermediate states of this protein. And of course, it has to be fast and extensive to unlock the exploration of the normal mode space and to go from the structure to the function. So for this, we created a set of 2D and 3D views to analyze the normal mode space and the protein. So on A, you have the 3D view, which represent the protein structure with different representation. Here you have, for example, a secondary structure. And also you have some global informations, for example, some glyphs that inform the user about the chosen normal modes. Then on B, you have a 2D view, which is more localized view with the influence of every mode on the selected tunnel, as you could see in the violet here. And you have in the matrix some tunnel property. And then you have some filtering, of course. And then on view D, the 2D view, you have the equivalent of the B view here, but for combined normal modes. So with all the combinations that can be selected into the 2D, the first B view here. So I will now describe the view quickly. And here I will start with a 3D view. So you have different properties or measurements that are drawn from the mode. So the first one here would be the correlation sticks in orange or yellow, as you could see directly on the 3D structure. So this would inform about the link between the amino acids under the normal modes. You have, of course, generated arrows. You can see in, for example, red or green here that will inform about the global motion of one selected normal mode on the protein structure. And then you have more localized information with color, for example, here with red on the right top corner, with red and blue, informing about the variants that are linked to one selected normal modes. And in the bottom right corner, you have some arrow glyphs informating about the direction of the movement of the normal mode on a more local scale. So, of course, in the 3D view, as I briefly introduced before, you have the trajectory reconstruction, which is the main advantage here, is to be able to see the protein moving on the normal modes. They are generated on the fly, and we generate several snapshots on both positive and negative directions, because as I mentioned, the normal modes is oscillatory motion, so we have a phase going in positive or negative directions. So to be able to see the tunnel moving in the 3D view, and a bit later, as I will introduce it, to have the tunnel properties in the 2D view, we need a tunnel reconstruction. So we devised our own quick and efficient way of reconstructing the tunnel under the normal modes. And why not using the standard or state-of-the-art method for tunnel reconstruction? It's mainly because we needed a very fast way of doing it, because we have to study the tunnel dynamics for every mode or combination. And also because we didn't want to have an issue with registration, as here we know the functional tunnel and we want to study the same protein void under for each or every normal mode or combination. So for this tunnel reconstruction, we here I schematize the tunnel in blue with a sphere. So we compute the surrounding amino acids that are making the tunnel walls. we displace them following the normal mode vector field. We displace the sphere based, or the tunnel spheres based on an average displacement of those surrounding amino acids, and we then optimize the largest possible radius for the tunnel spheres in order to displace the tunnel. So now I will introduce a more so the other views that are more on a local scale, and also as a small user study that was conducted at computational biology unit. So here we have the 2D view, as I briefly introduced before. So on the x-axis, you have every normal modes of the set. And then on the y-axis, you have the sphere number, which are composing the tunnel. So for example, the starting sphere and then the ending sphere. And then in the matrix, you have the different tunnel property that we measure as a color value. So here, the property that was shown in violet was the overlap, or we call it the overlap, but it's the normal mode influence on the tunnel. So that's our main property that we will use to link a structure to function through the tunnel. And so this overlap is basically computed as follows. We have the tunnel again with the surrounding amino acids again and the normal mode vector field. And then we devised an optimal vector field, which will translate into widening or closing the tunnel, which is, as I introduced in the motivation, the representation of a tunnel function here. So this vector field, for example, will be here as shown in red. And then we measure the similarity between the two vector fields in a way of quantifying the influence of the normal mode on the protein tunnel. So here we can see the values for this example and the protein we used. So here you have all the modes and all the values in violet, which show the influence of the modes on every sphere. And then we also added a way of ordering those modes, or actually selecting the modes that will represent a functional motion and not more locally more local modes. So the ones that will be directly linked with the function. And we added, so in the headers of the modes, a way of coloring this relevance. So here this coloring is also the influence of the normal modes, but not on every local sphere, but for the whole considered tunnel. So here in red, for example, at the far left, you have mode 7, which is the slowest mode and which represent the most impact over the whole tunnel. Here we also can, like I said, so we had the coloring, but we can also order the modes based on this overall influence. So here is to show the ordering. Mode 7 is still on the left, but then the other modes have been reordered. And for example, here on this use case, the end user could see that mode 19 and mode 13 here in the middle left part of the screen were more prominent than other surrounding modes. So meaning in terms of local influence, that they were more locally influencing the tunnel, but regarding the overall influence, they were ranked quite far on the right compared to mode 7, 9, or 8, for example. So the end user were interested in those modes. And they could also have access to other properties of the tunnel to decipher or to study them a bit more in details. For example, here I showed the tunnel sphere radius change. So with an increase in the radius in violet and a decrease in the radius in green under every normal modes. And we could see, for example, that mode 19 here that is highlighted shows an increase in the spheres that are in the midsection of the tunnel, which correspond to one of the active part of this selected tunnel. So it shows that mode 19 has an influence on the mode that could be functionally relevant. And of course, we could select this mode, as you can see here, and sort the modes this time, and with the coloring also, this time not on the overall influence of the normal mode on the tunnel, but on the as a other way of measuring the or exploring the normal mode space as the similarity between each and every modes with the selected one. So for example, here mode 19 is selected and mode 9 is the most similar to mode 19. So that's another way to probe this normal mode space with regard to the chosen tunnel. And of course, it's possible to use other properties, not only the overlap or the radius change, or sorry, of the radius change, but we have, for example, here the sphere radius of the tunnel. So here it's just the absolute radius of every sphere under the normal modes. And we have also the sphere fluctuation, which is the fluctuation value under the normal modes of the surrounding amino acid of a given tunnel sphere. So in combining all that, the end user could select a subset of normal modes. So with the most either relevant, with the most relevant on the tunnel or locally or globally, and the ones that were most similar with mode 19. For example, here mode 16 was selected. And then the user could go to the combined normal mode view, which is a focus on the subspace of the normal mode space, and to have all the possible combination with the 6 selected modes in the previous views. So here, for example, we saw, or the end user saw that the mid section of the tunnel, as highlighted here, was showing an increase or widening under only a specific set of or a specific combination of the normal mode, the selected normal mode set. So it was a way to narrow down the relevant normal mode set that will impact this mid section of the tunnel. And then, of course, they could go back to the 3D view and play the normal mode trajectory given this selected set to see the potential impact on the overall scale and on the given tunnel. So as a conclusion, we devised a tool for the analysis of large normal mode spaces for protein function. It's possible to explore the individual normal modes and their combinations. And we have a way to actually quantify and visualize the normal mode influence on both local and global scale. It could be a mean to link protein structure with function. And also as one of the requirements, and it was important, we have to start only from one loaded structure as input. So thank you for your attention. I'll be happy to answer some questions.
Thank you very much for the nice presentation, Pierre. And now for the Q&A, we also welcome Jan Byška as also an author of this work. And we have some questions from the Discord, and the audience is encouraged to ask further questions. So one question by Michael Krone is the following. He asks, this may be a bit off topic, but would it make sense to compare the results of NMA and an actual MD simulation of the same protein? And he guesses that this could show the differences of theoretically possible protein conformations from the NMA and the ones that actually occur under certain boundary conditions from the MD.
That's a very good point. And we also thought about doing this. The problem here is that for channels, which was our use case here, some motions could be very large amplitude and slow motions, we could call them, to be able to twist this packing of alpha helices to open or close the tunnel. And with MD simulation, they will be quite computationally extensive to detect, and also we will have to run a long molecular dynamics simulation. So using normal mode analysis was a mean to circumvent this shortcoming. And but yeah, as a way of assessing the precision of selecting this subset of normal modes, it could be a good way to compare with the trajectory or some snapshots of the trajectory with snapshots of either other conformation or either some given part of molecular dynamics simulation, definitely.
Yeah. Let's see, do we have other questions from the Discord? If not, you're encouraged to ask some. I do have a question, actually. So this is quite interesting research also from the setup, with you coming actually from the domain side, which is of course always a great starting point for research like this. I'd be interested in hear more about your point of view on what would be and clearly this is a research prototype, and it's a very interesting approach that you have explored there, but where would you see sort of more the day-to-day use scenarios of this approach? How would you see this employed in more of a daily practice kind of way?
It depends a lot on the use case, of course, but it could be, for example, when there are some protein channels where the opening and closing or conformations are not both available. So, for example, only the closed conformation is available, and opening the channel or getting the PDB structure and or a precise PDB structure for an opened channel is a bit harder. So it could be, for example, possible to load only the closed structure inside the tool and explore the normal mode space to try to reach putative open conformation of the channel, with the tunnel being the main one inside the core of the channel. That could be one use case. And I guess in a general way, it's more of an exploration tool. So to get, of course, not as precise result as molecular dynamics, because it's way more extensive and expensive also, and a quick way. So to have a quick way to probe the structural dynamics and with regard to the main tunnel.
Like following up on what you just said, actually, like what is your impression, again, using the opportunity that you are coming from a somewhat different background than we often have here, on the acceptance of these kind of more exploratory tools in your community? Is this something where there needs to be a lot of evangelism, or do you think that people are open with clearly something that may not correspond to their typical workflow so much?
That's a very opinionated question. I'm not sure I'm able to answer it. As for myself, and mainly in our group at the computational biology unit, we like to have a very quick and first way of exploration when we want to, for example, start a round of analysis. And running molecular dynamics, it becomes easier and easier with more computational power and also cheaper. But having a tool where computing the modes takes a few minutes and visualizing them is real time, like this one, it's a very good opportunity to you know, draw some insights or some guess. And also here I was mentioning that we have to know where the main tunnel is on the structure to link the protein structure and the protein function, and then to study its dynamic. But it's also possible to use the tool in the reverse direction, knowing that we have the protein structure, we compute all the tunnels, and then we select some tunnels and study the dynamics of this tunnel, of those tunnels under the normal modes, to be able to select one tunnel that would be of particular interest, for example. So that's something that is quick, efficient, and yeah, less expensive than molecular dynamics.
Okay, then I would like to say thanks to you, and of course to Karsten and Hannah for their great presentations, and thanks to the audience for their very lively participation in the discussion here in what was, I believe, a very strong and very, very interesting session. I think that's it from our side. There will be a short break until the beginning of the next session, and let's enjoy the rest of this conference.